Hello guys, today let's continue with dynamic programming problems. Again, we will continue until we master this. We master all dynamic programming techniques. And okay, so today's problem is longest common subsequence. So we are given a two integer arrays and we need to find the longest common subsequence. So a subsequence of an array is okay. First, let's for example an array like 1 5 6 3 8 and 4 3 9 8 2. So subsequent is element can be non-contiguous elements like one. So here the longest subsequent here can be 3 8 and 3 8 between the two arrays. Okay, so here is a dynamic programming problem. So okay, let's start with the example in the input. So we have two arrays of 1 2 1 1 2 3 4 and 3 4 2 1. So the LCS, okay, longest common subsequence, we shorten it to LCS, is 3 and 4. So the length is 2. So these are the common longest sequence subsequence. So we need to okay, so the naive method to find the LCS is that we for each array here and each array there, so there are a total of two to the end combinations, and here also to the end combinations. So to match, to find if each of these matches, it will take a two to the power of 2n, which is a slow to the power of 2n is very slow, so we need, okay, so let's okay, so let's try work through the naive string matching, naive subsequent matching, element matching. So first one here, I can match with 3 4 2. So the length when compared with 3 is 0, 4 is also 0. So when we let's take the one element here, the length is 0 when compared with 3, 4 when compared with 3, 4, 0 when compared with 4, and 2 is also 0, and 1. Okay, so we have 1 here, so the length when matching the first array with the length of 1 is longest is 1, LCS is 1, and next let's try with the array 1 2 1 2. So 1 here is also 0 0 0. Since the array 1 2 can be matched with 2 here, so the length here can be 1, and 1 2 here can also be 1. So when in compare with array of length of array that end at the index, let's go the index 1 2 and 3 and 4. So when we in the set index 1, we have the length is 1 here, and length at index 2 is also the length 1 1 2 is also 1. So next is when we insert the index 3, so 1 2 3. Okay, so this one can be a length of 1 when we compare with the arrays that end at 3, and when at 4 we can also reuse the value of 1 here, so the longest is also 1, and next is the 3. The 3 is okay, so, the 2 here, okay, we can match the 2 before, so we can take the result before, which is 1, and next is since we cannot match with anything, we can just take the result before, so that's 1, and next is when length is 4. So when we have the full length array, we compare this one with the 3, and we have length with the array that ends at 3, we have the longest length is 1, and when ends at 4, okay, so because 3 4 here we can 3 4, so the length is 2, and also 3 4 2. So we cannot match the number 4 here, so we will take the max of this, and max of this, so it will become max is 2 is 2, and next is also max of 2, and 1 is when we have the 1 here, we cannot match with any other array, so the longest sequence of the subsequence is also 2. Okay, so the LCS is here is 2, and okay, so this just looks like this example is too simple, So let's try another more complex example. So okay, so like let's try another one. So 158 6 9 9 13 4, and this one is 5 9 5 8 9 9 4 13. Yep. And let's calculate the LCS of this. So here we have array 1, the array 2, and the index is 1 2 3 4 5 6 7 8. Okay, so let's find the here is let's compute the longest common subsequent that by first is. So let's go with the computed array dp I. So dp is okay, so here dp is the array. Equal LCS that, and at index I. Okay, so dpi and z up array I and index z up array b. So here is a dp so when we calculate the dp I equal 1, and we take the first example, first value here, we can compare with our other values here. 1 with 5, so the LCS is 0. 1 with 9 is also 0, 0, 0, 0, 0, 0. Okay. Next is a DP 2. Okay, let's annotate it a bit clearer, more clearly. So the longest at the array 2 is 5. Okay, so 5 and 5 will match the value here. So the longest is 1, 5 and 9. We can take from the left value, so this it doesn't matter, but we can take the left value. So 1, 5. So 1, 1. Yes, it matches. So 1, 1, 1 and 1. Next is DP 3. So when we consider the 8 value 8, it doesn't match here, so you can keep the previous LCS, which is 1. This one is also 1. One here, 1, and oh, there's an 8 here, so we can take this one plus 1 equal to, so since we have 5 and 8 here, also 5 and 8 here, so the longest is 2, and next is we can just copy the value from the left, so 2, 2, 2 and 2. Okay, and next is DP4. So here is a 6 here. Nope, there isn't any 6 here, so it's just the same as the above. And 9. Okay, there's a 9 here. Okay, fine. So there is 1 and 9. So the value 9 is, it matches the AI matches the BJ. So the longest here is 2, 1 and 5 and 9. So same here, if we can copy the left value, so 2 and okay, so 5, 9. It doesn't match the fourth value, so just 2, 5, 2. Oh, so this one actually matches 9 here, so 5, 8 and 9. So the longest is 3, and here 2 we can copy the left value, so 3 and 3. Okay, so let's continue until we finish the DP, alright? So 9, 1. So it matches the value 9 here. So okay, see. 5 and 9, we can copy the left value and plus 1, or we take the value above. So here is 2, 2, it doesn't match this. 2, 2, 2. Oh, and it matches here. So 3, still 3, I think. 5, 8, and 9, 5, 8, 9. Yep, 3, and 3, and 3. Yep, nothing changes. DP 7, 13. Okay, so copy, 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 copy. Oh, but the 13 value here, it matches 13 here, so the long is 4. Next is a DP 8. Mm, 5, 8. Nah. Okay, so here is number 5. Eraser. We can copy the value 4 here. No. So 1, 2, 2. Three. Oops. Here should be 3. Sorry. 3, 3, 3. And okay, so here we can copy the left and plus 1 is, so we have 4, and here is also 4. Okay, so the general formula of dp is dp I j equal to dp I minus 1, the maximum of dp I minus 1 j so there can be some cases here. dpi minus 1 j or dpi I minus 1 j minus 1 or dpi minus 1 j minus 1 plus 1 if dpi I bj equal ij say bj equal I yep, so this is a total formula. And yep, so the formula is here, and now let's implement our code. So okay, int cs vector int const vector int a and const vector int b, so that n equal to I dot side. And let's create a dp array of length n. And finally we return the dp n minus 1. Yep. Okay, so let's input the arrays. Lesson plus plus vector in I equal b equal vector in and value is 0. And we return the LCS of A and B. Okay, so now let's implement the algorithm. Actually, we don't need a dpij array. We don't need a 2D dp array since we can like just copy the previous line value from the can copy the value from the previous line. So okay, so for now let's compute the dp array. dp high. So if I high and next is for each of the existing b value, if I equal to b say, then dp z equal to plus plus. Yep. Okay, let's make the dp array of layer n plus 1 so that we don't have to pass the value. Equal z plus 1. Yep. Yes. P z equal dp plus yep. dp is okay. And this one looks right. Let's try. Okay, so let's try. Let me test with the test guy from here. 8 1 5 8 6 9 9 13 4 5 9 5 8 5 9 4 13. The expected output should be 4. Wait, 5 5 9 5 8 Okay, so our formula looks incorrect. 9859. Oops, irrelevant values. 9859, 58. Thirty. 30. Yep, so the maximum value should be 4. So let's try. AI equal to BI. Okay, so let's print out the DP, right? Let's debug it. Not 3. Okay, so there's some it is wrong here. We don't want to take the left value. so I think we need a 2D DPU right here. And +1 like that. And +1, so yep. +1 and +1. And this one is DPI +1. Okay, DPI. Okay, let's use one index. Nope. Say yep. Should be like this. Nope. Yeah. This is the correct value, I suppose. +1. Oops. say +1. Yep. Something wrong here. +1. Yep. Oops, nope. Okay, so let's look at the DP right again. So here we can either we text from this above, take from the left. So the default is that we take the value from the left. Oh, we can take from, if it is equal, we take from the above and +1. Okay. One, 5, 8, 5. So you can +1 from here. Yep. Actually, we can dpi plus 1z. It also works too. Okay, so let's use this as a baseline. Yep. This is a DP formula. Sorry, I messed up the right so much. So okay, so we can either with plus one from the previous iteration, or we copy the left value, or copy the top value of the previous iteration value. So here it should be the correct answer. Submit. Yep, accepted. Let me validate with the Gemini AI for the optimal answer. Okay, so we can optimize by this. Okay, and let's mix it more clean. Minus 1, 5. Minus 1. Minus 1. Yep. And resubmit the answer. Okay, so this is a solution of the first it is quite complex. Actually not complex, but it's hard to visualize it in code. Okay, we have the first solution. So let's get to the first problem. So let's go to the second problem of today. Yet another build array problem. How many arrays A of length n consisting of non-negative integer that do not exceed k such that the sum of every two adjacent elements is a prime number? Array of length n consisting of non-negative integer. Okay, so let's turn on the timer for thinking and implementation. Array A of length n consisting of non-negative integer do not exist k sum of every two adjacent elements is a prime number. Okay, so we need to simplify this problem. So every two adjacent sum of two number is a prime number when okay, so first let's find the prime number, I think. So since we have an array of array is that n element, can k do not exceed k. So the highest value it can reach is k plus k. So for prime number, so with it we can find prime numbers that do not exceed k plus k. Okay, first we find the prime number that do not exceed k plus k. So the max is the first 2000 prime numbers. Okay, so generally they are average of a square 2000 prime numbers. So like 15 prime numbers. And we need to find a way to so that the array has n values. Okay, first up, let's process in our okay, so let's first primes with the boolean prime length n equal so let's take in n and k the boolean up is prime equal mass up k sẽ cái multiply by 2 okay. Values. Each one of those is true. Is prime. So equal plus 1. False. Let's use the we need to, so this is a prime sieve. Multiply by some equal false. Not prime. Continue. Yep, and we return prime. Prime. Okay. see. This one works correctly. Okay. Next is that we need to find some. So that once we have find the price, we need to find some equal to any of the price. So we want to count how many sums that equal to a prime. Okay, so for example, for an array of 6 elements, you can have this, and this. X1 equal to a sum. So sum. You need to count the number of sums. Okay, so let's say for a value x, how many way for an x, how many ways? How many ways to some primes? Okay, so maybe I'm getting clearer. So we can for example we take an example x and we can find all the primes that are greater than x. We can use a prefix sum to count the number of primes when we are at the value x. So we have a counter of every number. So at 0, then there can be okay, so we can populate the array here. So at 0, at index and here is this index 0, and with value 0, we can find primes of 0 to transition to any other values here. Let's say with 5 primes, less than primes, less than okay, so let's say for first index, if we get the primes move, nope, nope, then they must be at least 2. So if the value of I is currently 0, and we need to find how many index that can be created from 0, then okay, let's count. How many index from the value 0 to k? How many primes from 0 to 0 plus k? And we get the first case. Next is even it is 1. Okay. From k to k plus k. Yep. And how many prime is a summation of this? Let's find the summation of this. Nice is that we at the index 2. At 3, 3. How do we deduct the value? Shit. How? Okay, so there are only possibilities from here. Okay, so we can only count the possibility here, possibility here. And from here, there. How many priors from that value to so 0. So this the summation must be a prime here. So the prime summation and plus something to produce more primes. Okay, so we need to produce something to create primes. Fuck. Primes. How to find more prime numbers? So at 3 here, there is a constraint that we can only take the okay. So before is a primes plus something value. So this one, okay, this one must be a prime, and plus something to create a primes. too difficult. That is so seed stuff. Okay, we have the base cases here. And now we need to like okay, so let's revisualize 1, 2, 3, 4. So here we have 0, 1, 2, 3, 4, 5. The big count. So plus k. And we have list of price. P2, P3, P4. Okay, so we will have a set of price. it again. How do we multiply? Okay, so at most there are 15 primes for x value. Okay, so there are n. We need to iterate the steps. So so we have maximum of a value is k. So we need to find how many prime from a state of k to the next state transition. So for x they are like k multiplied by square root of k multiplied by n and 1000 multiplied by so like 2000 multiplied by 2000 multiplied by n, which is 100. 8 million, 8.8 million. Yeah, it can run. Yeah, it's just 8.8 million. Operate. Okay, it is really dumb, but let's do it. Okay, so we need to find how many ways to sum until the end index to equal to 0, 1, 2, 3, 4, 5. Yep. What? So there's okay, so from a value n, let's find the next primes. So let's have a vector. A vector of my integer. So, possible price from 0 can be k multiplied by 2 vector in. Yep, just leave it blank. In equal to 0. Okay, minus 1. Less or equal than k. I plus plus for z less or equal than k. Plus, yep. Possible price plus z. Plus back. Plus z. Yep. EB is a primes and okay. We have the next possible price for every k, for every, yeah. So now let's iterate. I think okay. If n equal to 1, okay, plus 1. Yep. So otherwise we need to build a DP, alright? How to build a DP, alright? So okay, so let's build a DP, alright? In DP copy hợp lang cap and vector in so okay plus 1 0 okay plus 1 yep so far let's build the build base okay result then the result I less or equal than k I plus plus rest possible prime in mode in A in B 10 time depth 10 yep should be dp and plus yep and of the base k in dp equal to 2 yep dp equal to surprise account. Yeah. Yep. Say equal to Z plus plus. Yep. Continue. Possible primes of J. DP prime. So from the value oh not can have how many possible primes? Okay, so more possible primes. Prime. So say Is this correct? I think this should be. Oh, let's try this. I think this solution might be correct. Oops. Customer brand. It might not exist. Okay, so the base case is correct. I-1 Z. Okay, +1 seems personal price. Oh, okay. It's wrong here. then equal primes minus dp. And then equal edit. Oops. I think this is right. Let's try it. Submit. Yay! Our answer is correct. Okay, so let me explain my solution. Okay, let's simplify it. Okay, so yeah, let's start from this. We can DP by having two dimensions. First is how many. The first dimension is at how many. First dimension is at how many. Which number of prime integer? No. Okay, so the first dimension is at how many integers, the number of integers in our array, and the second dimension is at which value it is currently at. And okay, so here, so the D1 is dimension number 1. Okay, D1 is how many values is no, this goes the array length. D2 is current. No. Submission up this minus 2 value equal ways to create array. So okay, so elements. Number of ways to create such arrays. Okay, so the DP array is at the okay, first is the first dimension. We store the array length. The second dimension is the current sum of the last two elements, and the sum and the value dimension is the number of ways to create such arrays. So for the base case, we can start with a 2 and we count how many ways to create arrays that has sum of 0, 1, 2, 3 until k. And from 3 we can find how many ways to create array of to have the array that has sum of 0, and from the previous values. So okay, so from the previous value we can find the branch of previous the previous array, the previous state array length, and multiply by ways to create of that length. So the previous price and ways to element value. Okay, so I describe the DP array incorrectly. So the first dimension is array length, and the second is a last element, the value of last element. So, and the value is the number of ways to create arrays of length d1 with that ends with a d2. So with the base case here, we can calculate how many primes that can be created from two values. From 0 we can create how many primes? One, two, three, four. Okay, and we count the number of, we have the number of ways to create post arrays that ends with d2, and with the last element value. Okay, so from that element value, we can, for each possible price of the to transition. Okay, so it is like this. Value plus x equal next price so the previous value plus x equal primes. So the next, so we can find how many we can have. Okay, it is difficult to explain. I wish I could explain this. So okay, let me consider again. Okay, so dp dimension 1, dimension 2, value. Okay, so from the value x, let's for example from the value x, we want to the array to be to satisfy the requirement that the sum of two adjacent elements is a prime number. So we need to plus a value y to create a prime. Okay, so we can find all the y's that are less or equal than k. That we can plug the y value here to write to the dp array. multiply by the ways to have x as the previous. So okay, so for x y value, you can use a number of ways to have x as the previous value. So dp, you can create like this. You can find all the next primes from the previous prime value. Previous value, not prime. Go to next one. Prime. Okay, so the value is this. Wow, it's really hard to explain with words. Okay, so this should be okay. So we create a DP array of 2 dimensions, D1 and D2. The first dimension is the length of the array. The second dimension is the value of the last element, and the value of the DP array is the number of ways to create arrays of length D1 that ends with value D2 that ends with the D2. So the DP array of D1 and prime adding is the sum of our previous the sum of our DP, the previous length DP arrays where the dimension 2 plus the prime addend equal to prime. Okay, let's rewrite. This should be the whole. Okay, so yep, we iterate from 0 to k, and for x we check if the current value I plus the prime addend equal to a prime, then we can calculate the dp of the current array length and the prime addend as the number of ways of the previous I of the length the previous length and I. Okay, so let me update okay, and we are done here. Wow. Sorry, I couldn't describe the DP space cleanly. I couldn't describe clearly. But okay, so this should be the safe. Okay, we find the prime, we count the primes, and we use it as a DP counter. And that's all. Thank you.